In this discussion, we will talk about logarithmic differentiation. Sometimes we can use the properties of logarithms in order to simplify the differentiation process. The specific properties of logarithms that we will use are the following. Log of any base of a product is equal to a sum of logs in which the two factors of the former argument are the new arguments. We will also use the property that, or we might, depending on the example we use, but this is a frequent property used, is that the log of a quotient is equal to a difference of logarithms. And that the logarithm of an exponentiation, such as if the argument was m raised to the p exponent, that's equal to p times log base b of the former argument without the exponent. So we'll be using those properties of logarithms in order to help simplify the differentiation process. Let's look at this problem here. We will start, we could of course apply the product rule combined with the chain rule to differentiate. But we're going to try to simplify the process a little bit by first taking the natural log of both sides of the equation. So we'll make both sides the argument of a natural log. So all we've done at this point, we certainly haven't differentiated yet, all we've done at this point is to make both sides the argument of a natural log. Now, however, we're going to use properties of logarithms to simplify this right side. We see that we have a product, this binomial to a power times that binomial to a power, so we'll write that as two logarithms. We have the natural log of the first one, 5x squared minus 3x to the fourth, and we can add that to the natural log of 2x cubed minus 7 to the fifth. And then we can also take these exponents and put them out front, so we will do that. That's a property of logs. If you have your argument is raised to an exponent, you can bring the exponent out and make it a factor times the logarithm, and the argument is the same as it was before without the exponent. So here we'll have 5, because the exponent is 5, times the logarithm without that exponent. So 2x cubed minus 7. Now we will differentiate implicitly. Well, when we differentiate the natural log of y, we simply get... Oh, we need to move it up. When we differentiate the natural log of y, we simply get 1 over y, but remember, when you differentiate implicitly, you have to throw in a dy dx or a y prime. Here, we're going to have 4 times, we're differentiating this, so that's going to be, remember the rule for the natural log function, you just write down the argument in the denominator, then you take the derivative of this denominator and put it in the numerator, so 10x minus 3 plus 5 times, write a ratio, 2x cubed minus 7, the argument of the natural log goes in the denominator, and then the derivative of this, 3 times 2 is 6x squared in the numerator. Now we're trying to solve for y prime. We're trying to differentiate the original function, y. So we will have y prime if we multiply both sides by y. So we will do that. Y prime is equal to y times this whole other side over here, which is, let's see, we'll call that 4 times 10x minus 3 over 5x squared minus 3x plus 5 times 6x squared over 2x cubed minus 7. Now we're almost done, but we will recall that we had y in terms of x, so we will substitute that in now on the last step. y prime is equal to y, which was that complicated expression we started with. Remember, it was 5x squared minus 3x to the 4th times 2x cubed minus 7 to the 5th, and that's our y right there, and it's being multiplied by this pair of fractions here. So we'll write that in and we'll be done. I guess I'll go ahead and admit that 5 times 6 is 30. So we have 30x squared over 2x cubed minus 7. And there is the derivative. It's